In this video, we're going to learn how to solve exponential and logarithmic equations, namely equations that contain either a logarithmic expression or an exponential one. We start by focusing on the three strategies that we're going to employ in solving these equations. The first strategy is based on the one-to-one property that both the exponential and the logarithmic function have. So what is a function that is one-to-one? Let's recall that a function that is one-to-one cannot have two x values, say an x1 and an x2, that are being mapped to the same y value. So a one-to-one function needs to avoid this scenario. So we're going to now use this both for the exponential and for the logarithmic function to deduce a strategy to solve an equation. So if you encounter an equation of the form where you have a raised to some x1 and that equals to a raised to some x2. Now what is going on here? I'm telling you that given an x1 and an x2, their corresponding y's, namely in this case for the exponential function a to x1 equals to a to x2. So for two different x1 and x2, we have that they are mapped to the same y value. And since this cannot happen for a one-to-one function, the only conclusion that I can draw to make sure that the exponential function is still one-to-one is that to start off with, I had the same x values, namely x1 had to be the same as x2. So if you have an expression a to x1 equals to a to x2, then you can immediately conclude that the x1 input is equal to the x2 input. Similarly, if I have a log base a of, say, x1 equal to log base a of x2, for the same reasons, since now also the logarithmic function is one-to-one, the only way this can happen and still ensure that the log function is one-to-one is if x1 equals to x2. So if you have a log of x1 equals to a log of x2, you can conclude that their inputs, x1 and x2, have to be equal to each other. Our second strategy relies on the definition of the log. If we have that log base a of x equals to y, then by definition we can rewrite this in exponential form and have that the base a always stays as the base, now raised to the output y equals to the input x. Remember, since the exponential and the logarithmic function are inverses of each other, the way we go from one form to the other one is we simply interchange the input and the output, namely the old input x becomes the output and the old output becomes the new input. So we have that a to the y equals to x. Finally, the third strategy relies on the most important property of the log, namely that if you have the input of the log, say a raised to a power, say c, then what we can do is pull the c in front of the log, and we're just going to get c multiplied with log base a of capital A. So in essence, again, this is why we love the logarithmic function so much, we can pull the power from the input in front of the log. So these are the three strategies, the one-to-one property, the definition of the log, and the property of the log that we're now going to use in examples to solve various exponential and logarithmic equations. So let's first look at the example 2 to the x equals to 32. Again, the variable happens to be in the exponent, so we can't really free it up unless we use one of the three strategies I had just mentioned. So we're going to try to rewrite this expression as a to the x1 equals to a to the x2. So we're going to try to rewrite the right-hand side here as 2 raised to a power. So let's see how we do that. Well, the left-hand side stays as 2 to the x, and 32 happens to be 2 raised to what power? Well, 2 squared is 4, 2 cubed is 8, times 2 is 16, so that gives me 2 to the 4th. 2 to the 5th is 32, so 32 happens to be 2 to the 5th. So now you notice I have the same base 2 that is being raised to the power of x and to the power of 5. So by the 1-to-1 property, we can deduce that x equals to 5, right? The inputs for the two functions are the same, and that is the solution for my equation. Let's say now that we look at an example where we have a logarithmic function. Let's say ln of x minus ln of 3 equals to 0. Well, we immediately recognize that we're in fact dealing with, again, a one-to-one scenario, only in the case of the logarithmic function. If I bring the ln of 3 on the right-hand side, now I have the log base e in both cases of x equals to the log of 3. So again, I'm dealing with the one-to-one property here. And so I can conclude that the two inputs, namely x equals to 3, the two inputs are equal. And this is the solution for this equation. The next example gives us 1/3 everything to the x equals to 9. Now this might not be as obvious that it really will be the same thing. We're going to use this one-to-one property to solve, but if I think about it, how do I write 1/3 to the x as a simpler expression? Well, I can rewrite the right-hand side here as 1 to the x, or just 1, divided by 3 to the x, which is 9. And now, because I realize 9 can be written as 3 squared, I also want to write the left-hand side as 3 to a power. How do I move 3 to the x from the denominator in the numerator? Well, I pick up an extra minus, so I get 3 to the negative x equals to 3 squared. Again, the same scenario now, 3 to a power equals to 3 to a power, so I have the one-to-one property, and I can set these two quantities now equal to each other, and I get that negative x equals to 2, or the solution of the equation is that x equals to negative 2. Looking at the next example, we note that we really can't use the one-to-one property here. Why? Well, while on the left-hand side I have e to the x, so the base is e, the right-hand side really can't easily be written as e to a power. Namely, 7 is not e to a power, at least not something that we can compute in our heads. So unlike the scenario that we had before, where we had 3 to the x equals to 9, this 9 could easily be written as 3 squared, and therefore I could use the one-to-one property. Here, however, that's not possible, so we have to use another strategy. Well, we're going to use the strategy of the property of the log. So when you have these expressions when you can't rewrite one of the sides as the base e to a power, what you're going to do is you're going to apply log to both sides of the equation. When it comes to logs, we need to decide what base we're going to have, and you're always going to choose whatever bases you have where the variable is. So we're going to apply, in this case, log base e on both sides. So I'm going to write the log base e, which in our notation is ln of e to the x, and this is going to equal to ln of 7. Now, why was this useful? It was useful because now at this stage I can use the property of the logarithmic function, namely I can pull the power of x in front of the log and get x multiplied with ln of e equals to the right hand side ln of 7. And now I'm done. Why? Because by the way I constructed this log, it was the same base as what I had under my expression here, e to the x. I set it up so that this turns into ln of e, and e to the first is e, so ln of e is 1, so the left hand side is just x, and now I have isolated x by itself. I have that x equals to ln of 7. Finally, let's look at an example with our third strategy, which is going to be very clear to denote. This is the strategy where I have log on one side of the equation but not on the other one. So again, we can't use the one-to-one property for the logarithmic function. So what we're going to use instead is the definition of the log, our second strategy. So what I have here is log base 3 of x equals to 4. What I'm going to do is I copy the base, that always remains the base, and now I raise it to the output equals to the input. So 3, now the old output becomes my input, and then the x, the former input, becomes the output. And that gives me the answer, namely I have that x equals to 3 to the 4th, which happens to be 81. Looking at another example, let's say that I have log of x equals to -1. Now, what does this log of x represent? Remember, when the base is not written, then in essence this is just going to be log base 10 of x equals to -1. Since we're going to use the definition of the log here, it's important that we understand what basis we were working with. In this case, it is 10. So let's just rewrite this expression in exponential form. So I'm going to have 10, the base, raised to the output of -1 equals to x. So x happens to just be 1 over 10, and this is the solution for my equation. And very similarly, if I have the ln of x, in this case, what is the base of this logarithm? It is the number e, so I'm going to have that e cubed equals to x, and this is the solution for my equation. Again, when you have a log by itself and the right hand side is not a log, then this is the strategy that you have to apply. You have to rewrite the logarithmic expression as an exponential expression. And now let's consider a series of slightly more complicated examples. However, you need to find a way to bring these equations back to the simple three strategies that you learned. So if you practice the really simple equations, then you should be able to just recognize the strategy you should employ here so that you turn these more complicated equations into the ones that you're familiar with. So for example, if I have e to the x plus 5 equals to 60, bringing the 5 on the right hand side will turn this equation into e to the x equals to 55. And now this is a classic scenario of an equation I should be familiar with. Namely, I need to apply log on both sides of the equation so that I can free that x up. So I'm going to apply log, namely base e. So ln of parentheses e to the x will be equal to ln of 55. Don't forget to apply the log on both sides of the equation. And now I can pull the x in front of the log and get x multiplied with what's left over, namely ln of e, equals to ln of 55. So my final answer, since ln of e is 1, I get ln of 55 for my x. Another equation, let's say that I have e raised to the power of negative x squared equals to e raised to the power of negative 3x minus 4. Now, while this has certainly very complicated exponents, just recognize it as e to a power equals to e to a power. So we are in essence dealing with the one-to-one property. So we can simply set the inputs equal to each other. And thus I'm turning an exponential equation into a simpler equation. Namely, it happens to be a quadratic equation. Let's bring x squared on the right hand side. And I get that x squared minus 3x minus 4 equals to 0. So I've turned an exponential equation that was complicated using the strategy that we had, the one-to-one property, into a simple quadratic equation. And now this is something that I know how to solve, namely give me two numbers that multiply to negative 4 and add to negative 3. So I'll have x plus 1, x minus 4. And so I have the two solutions. X1 is negative 1 and x2 equals to 4. So let's look at another example. Let's say that I have 3 multiplied with 2 to the x equals to 42. Again, this is a slight modification of an example that uses the 3 strategies. So let's see what we can do. Well, you always want to revert back to that same old scenario. So in this case, if you divide your expression by 3, you obtain exactly that, namely 42 divided by 3 happens to be 14. So now you have, again, one of these simple scenarios where you have to decide what kind of strategy to employ. Well, what we need to do is to free up that x, so we're going to apply log to both sides. So I'm going to apply log base, well this is base 2, so base 2 of 2 to the x equals to log base 2 of 14. Now the reason I applied the log was so that I could free that x up, so I can bring it in front of the log using the property of the log. So I get x multiplied with log base 2 of 2 equals to log base 2 of 14. And since log base 2 of 2 is 1, I now have that x is log base 2 of 14. Again, I was able to bring my equation down to one of the standard forms, and since I know how to solve that, I should be able to recognize how to get from this scenario to the simpler scenario. Looking at one more example, let's say that I have log base 3 of 5x minus 1 equals to log base 3 of x plus 7. So in this case, we recognize a standard classic scenario of the one-to-one property. So what I'm going to do, since the logs are the same base, I can just set their inputs equal to each other, and I get that 5x minus 1 equals to x plus 7, which simply gives me, if I bring x on this side, I get 4x, 1 on the other side, I get 8. So I get that x equals to 8 divided by 4, which is just 2.